So next addition reaction is the hydroboration reaction. In hydroboration reaction, the carbon-carbon double bonded compound. So in hydroboration reaction, alkene react with diaboranes. Hydroboration reaction, alkene react with diaboranes to form trialkyl borane. Alkene react with diaborane to form trialkyl borane, and this trialkyl borane on further reaction we use alkaline condition. In further reaction, this diaborane gives alcohol. So this is the simple process of hydration of alkene via diaborane. Via trialkyl borane. So this is the alkene when treated with diaborane to form trialkyl borane, and which on further treatment gives alcohol. For example, just we have taken here propylene. This propylene when treated with diaborane BH3 twice, we obtain trialkyl borane, tripropyl borane here. CH2 3B. When this hydrolyzed, then we get removal of this borane and we get 3 moles of CH3 CH2 OH, 3 moles of propanol we obtain. So this is general reaction of hydroboration. Alkene reacts with diaborane to form trialkyl borane. Here this propylene react with diaborane to form tripropyl borane. We get propyl alcohol, or say propyl alcohol we obtain. Let's see the mechanism of this reaction. In this mechanism, if we observe, this mechanism is takes place according to the Markovnikov's rule. Because addition of diaborane takes place via Markovnikov's rule, that is negative part of the reagent attaches to the carbon atom which is having less number of hydrogen atom. If you observe the mechanism, see the step CH3, here CH double bond CH2. When we use diaborane is B2H6. See one borane compound containing 3 hydrogens. So this negative part, this is positive part of the reagent. So negative part attaches to that carbon atom. So this negative part attaches to that carbon atom which is having less number of hydrogen. And this, see, 3 moles of alkene are required. 3 moles of alkene required for this reaction. So 3 moles of alkene required. Here we use first mole, where 1 hydrogen transferred here and attachment of borane here. So we get CH3 here, CH3 here is CH, and attachment of another H from this borane, and then CH2 and B, and these 2 hydrogens. Okay. In the similar way, another 2 molecules attached, 2 molecules of alkene attached, we get the product here, C borane, here CH2, CH3, another CH2, CH2, CH3, and here CH2, CH2, CH3. In the same way, 3 hydrogen transfer to 3 alkyl groups, and we get the trialkyl borane as an intermediate. So this is trialkyl borane as the intermediate. As we saw, this tripropyl borane, this trialkyl borane obtained here. This trialkyl borane, when further reacted, the removal of boron and attachment of OH is there, and that's why we obtain 3 moles of CH3, CH2, CH2, OH. So alcohol obtained in the process, and indirectly what? From alkene we obtain alcohol. So hydration of alkene takes place via diborane. So this is hydroboration reaction. One important point to remember, this hydroboration reaction. Another important point to remember, that point is, this process is also syn addition. Because if we see, this is syn addition. Why syn addition? Because when this double bond CH2 and we use diborane, we get the intermediate. The first mole of hydrogen added, first mole of borane added, then we get the intermediate, that is CH3. See here CH, and this hydrogen added here, and see CH2 and this borane with 2 hydrogen. So this is not cyclic intermediate. This is actually not cyclic intermediate, but cyclic like intermediate form, and due to this cyclic like intermediate form, this addition is a syn addition. Of diborane. Now remember last reaction, that is cis hydroxylation. The limitation of cis hydroxylation. One point to remember about cis hydroxylation. Cis hydroxylation takes place by using KMnO4 and osmium tetroxide. So this cis hydroxylation, what happens? We get the diol formation. Suppose that we obtain such type of diols. What is the disadvantage of this? This reaction cannot stop at the diol stage. It is difficult to stop the reaction at diol stage. Further oxidation, this product of reaction, diol product, is susceptible for further oxidation. This product is susceptible for further oxidation, and due to further oxidation, it is converted into aldehydes or ketones, and again further oxidized to acids. So further oxidation due to KMnO4 or osmium tetroxide takes place, and we get the acid product. So acid product obtained here. So sometimes they may ask the question, what is the disadvantage? What is disadvantage of cis hydroxylation, or disadvantage by using KMnO4 hydroxylation or diol formation by using KMnO4 or osmium tetroxide? So the answer for this question is that it is difficult to stop the reaction at diol stage. It further oxidized because this is susceptible for oxidation by using KMnO4. These are strong oxidizing agent. So by using this oxidizing agent, the reaction cannot stop at this stage, and it further proceeds. This reaction further proceeds up to the highest oxidation and acid obtained in the process. So this is the disadvantage or the limitation of cis hydroxylation. And what is the positive point or advantage of this reaction? We add 2 two hydroxyl groups from the same side if we want, and to the opposite side if we want, by using per acids. So this is one question about the hydroxylation. We saw hydroxylation as well as hydroboration reaction. Next important reaction, addition reaction of organic chemistry, is the hydrogenation. Hydrogenation is the another important addition reaction. Hydrogenation is what? It is the simple reaction where addition of hydrogen to carbon double bond to obtain alkane. Means hydrogenation is the simple process by which we obtain alkane from alkene. This is the important reaction of organic chemistry where we get alkane from alkene, that is saturated hydrocarbons from unsaturated hydrocarbons by using hydrogen. But this is not as simple as we see here. Just add hydrogen and two carbon double bond and we get alkane here. This is not as simple as we think. In this process, there is a requirement of catalyst to perform this reaction. So some catalysts are required, such as platinum or nickel. These catalysts are required to proceed this reaction. Without these catalysts, the reaction is not possible even at elevated temperature. If we increase the temperature, then also this reaction is not possible without the catalyst. So catalyst lowers the energy of activation, provides surface for the attachment of this H2 as well as attachment of this carbon double bonded compound. So it provides surface and also detachment of the product from the surface. So all these facilities provided by these catalyst. So this catalyst is required in the process of hydrogenation. So see why this hydrogenation is not possible without the catalyst. Without catalyst, it is not possible. Why? Because as we see the potential energy diagram or the progress of reaction, as the reactant is here and we get the product, then this reactant to product, as the product energy is always less and reactant energy is high, but the process to convert from reactant to product takes place via some transition state, and transition state, to go up to this transition state, it requires some energy of activation. And this energy of activation is not only provided by heat only. If we heat this compound, then this reaction is not possible by just using heat only. So if we observe the energy profile diagram for this reaction, then from reactant to product, energy of activation is there without adding catalyst, and if we use catalyst, then this energy of activation is decreased here. So this is energy of activation by using catalyst. Energy of activation by using catalyst, and this energy of activation without catalyst. Okay, so this is energy of activation without catalyst. This is energy of activation by using catalyst. It lowers the energy of activation. How it lowers the energy of activation? It provides surface to these reactants. Both reactants attach to the surface, and that's why addition is easy, and that's why energy of activation gets lowered. So if energy of activation gets lowered, then reaction is easily possible here. So reaction is possible easily here at lower energy of activation. Here higher energy of activation is there, and that's why this reaction occurs only by using the catalyst only. Okay, not directly by simply addition of H2. So what is the role of catalyst? See a role of catalyst. See the role of catalyst. So catalyst, what is the role of catalyst? Catalyst lowers the energy of activation. Lowers the energy of activation. It lowers the energy of activation. Lowers the energy of activation. Second, provides surface for the reaction. Surface for reaction, and it remains unchanged at the end of reaction. Remains unchanged at the end of reaction. At the end of reaction. So catalyst lowers the energy of activation, it provides surface for the reaction and remains unchanged at the end of reaction. So these are the roles of catalyst. So it requires for this reaction, and due to these roles, see the actual mechanism how this catalyst. Suppose that this is the catalyst surface, the platinum or nickel surface. To this surface, first the hydrogen attached here at this surface. This surface, attachment of hydrogen is there, so splitting of hydrogen there, hydrogen splitting, and we get attachment of the alkene compound. Now the probability of addition goes on increasing by catalyst surface, because the attachment of the alkene is here, attachment of the reagent that we want to add here, this reagent is there, and the addition of these hydrogens takes place here. Addition of hydrogen takes place, and we get the formation of product here. See, formation of product. So formation of product, attachment of these two hydrogen, and finally the catalyst surface. Finally, the surface of the catalyst remains unchanged, and there is a detachment of product. Detachment of product from the surface of catalyst. So we get the free product here. Okay, so we get free product here, and this is possible only when we add catalyst surface. So catalyst surface added here, due to which this reaction is possible, and in this reaction we obtain saturated alkanes. Alkanes here in this case. So hydrogenation is the important reaction where we obtain alkane from alkene by addition of hydrogen in presence of catalyst. In presence of catalyst, this reaction is possible. Why? Because instead of without catalyst, this reaction is not possible, because energy of activation is higher for this reaction. Energy of activation is higher. That's why this reaction is possible only with the catalyst, because catalyst lowers the energy of activation and provides surface for the reaction. At the surface, the reagent as well as this alkene attachment takes place. Due to this attachment, the addition is syn addition again, because these hydrogens, this carbon-carbon double bond attached to the same surface, and that's why the hydrogen addition from the same side takes place, and cis hydrogenation takes place. So this addition is also syn addition, where hydrogenation takes place, and it is important reaction in organic chemistry, because many times there is a requirement of conversion of unsaturated system into saturated system, and this is possible by using catalyst. So this is hydrogenation reaction. Now next, that we have to study another reactions, another addition reactions from this topic.